How's it going, everybody? We are gonna pick things up today from where we left off before. But before we do, the last thing we did was we talked about the definition of an acid and a base, the two methods. The Arrhenius acid and base. Basically, an acid makes a hydrogen ion. A base makes a hydroxide ion. That's it. That's all there is to it. And the other method that we talked about was the Bronsted-Lowry. That's where you have an acid donor. That's an acid. It like gives it up. And you have an acid, a hydrogen acceptor, something that gathers up a hydrogen. And we call that a base. And remember, if it starts on this side as a hydrogen, or I'm sorry, as an acid, on the other side, on the product side, it's going to be called the conjugate base, because when it goes backwards, it does the opposite, right? So if you start with an acid, it's going to be a conjugate base. If you start with a base, it's going to be conjugate acid, right? Because it's doing the back, you know. Remember, Bronsted-Lowry, only for when there's equilibrium things there. Equilibrium stuff going on. Also, what I'm not seeing from a lot of people are the handwritten notes. So the homework has two parts. There's like the homework thing where you like look at the homework packet. Like, remember a few days back I uploaded all the homework for this chapter. So I need the answers to those homework worksheets, and I also need to see handwritten notes for this chapter. That's part of the grading assignment. So don't forget to write down a handwritten copy of these notes. I need to see it. It'll just make me feel happy, like there's learning and stuff going on. So let's get at her. Because today, building on defining what an acid and a base is, today we're going to talk about what makes a strong acid versus a weak acid. And same thing with base, because it's not quite as clear as it may seem. Because there's like there's normal people speak, and then there's like, you know, the way scientists speak. So normal people will say things like, wow, that's really strong, speaking of things like Kool-Aid, and really what they're trying to say is that it's concentrated, it's very concentrated. There's a lot of solute dissolved in the solvent, which is not the case with acids and bases, because they actually come in two separate categories. There is a strong acid or base, and there is a weak acid and a base, and it's not concentration. It's actually the way that they behave inside liquid. So let's dig into it. A strong acid or base, what makes it a strong acid or a base is this thing, like bam, boom, bang. It dissociates completely in water. In other words, so here are my two examples down here. This first one, right, you know, is with water and HCl making hydrochloric acid. Look right here. You guys see that? Bam! It's a one-way arrow. So in other words, when we dissolve HCl, hydrogen chloride, in water, it makes a hydronium ion and a chloride ion, and that is all. Thank you much, once and done. It doesn't go backwards. You see that? That's why there's that one. Sorry, man, my cats are tearing apart my house. So that arrow means it goes one way. It is not a reversible reaction. So once this hydronium ion is formed, dude, it's there. It's just formed. Same thing with the sodium hydroxide. We call sodium hydroxide, we call this a very strong base. Again, not concentrated, but it itself, like the substance, sodium hydroxide, we call that strong because when we dissolve it in water, it makes, bam, sodium ion, and bam, a hydroxide ion. And if you look at this, bam, 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 right there, that is a one-way reaction. It doesn't go back and forth. So once we have this that hydroxide ion formed, it stays in solution. There it is. It doesn't magically disappear, nothing. Does that make sense? So when we say strong acid or a strong base, what we're talking about, now what we mean from the science perspective, is that when we dissolve it in water, the ions break apart and they stay apart. It's a one-way reaction, right? So, you know, same thing, only different. A weak acid and a base, they do not break apart completely, right? They only partially dissociate. It's called ionization. And here we have two examples. Dihydrogen sulfide is at equilibrium when you dissolve it in water. It makes two hydrogens and one sulfur ion. But this is the clutch thing right here. You see how that's an equilibrium symbol? What that means is the hydrogens break off, but they go back together, right? This is a reversible back and forth reaction. So once this stuff makes hydrogen ions, they're not always staying as hydrogen ions. Sometimes they go right back into the H2S, which is not making an ion, so it's not really acting like an acid. It's only like a part-time acid. This only acts like an acid when it's over here on the product side. Do you guys get what I'm saying? When it's over here on the reactant side, not so much. Not so much an acid because there are no hydrogen ions. Same thing with this Jimmy John right now. If you notice, when we put this stuff into water, oh look over here, it's producing a hydroxide ion, which is a base, but this is your clutch thing. I'm pointing to the screen so you can see this right here. It's an equilibrium, right? It's a reversible reaction, which means it's only over here making hydroxide like part-time. It's only a partial like base. It's also over here where it's like not base. There's no hydroxide ions over there. And this is the thing. That's why we call these things weak acids and bases, because when we put them in water, they're only acting like an acid or base like partially, like part-time. And really it comes out to be about only 30% of the time are acids and bases actually broken apart, making hydronium ions for acids and hydroxides for bases. So they don't fall apart completely. They kind of like go back and forth. We all know how this goes. Everybody knows this. This is like easy. So look. This is the thing. This word right here, concentration, that is not what determines whether an acid or a base is considered to be a strong acid or a base. Because we can tweak the concentration of something all over the place. It's not going to change its like strength. So concentration alone does not determine the strength of an acid or base. It's the ability to dissociate in water to form hydrogen and hydroxide that determines the strength of an acid or base. For example, if we took hydrochloric acid, good old HCl, and we had it at a comparable concentration to as we do, say, vinegar, right? Vinegar is yummy and delicious, and you pour it on our salad with Italian dressing with herbs and spices, and it's just, it's so good. Put on hoagies and stuff and your French fries. It's so good. The reason why it's so good is because it's only acidic like 30% of the time. Acid is considered a very weak acid. Vinegar is considered to be a very weak acid, so it's only like occasionally making a hydrogen ion. Most of the time it's all put together, but then hydrogen breaks off and it comes right back because it's a system at equilibrium. So over at the hydrochloric end, if we had them at the same concentration, we could not eat that hydrochloric acid, right? You can't put that on a salad. You can't put the same concentration of hydrochloric acid on a salad, because what you end up with is like a bowl of green goo, and you can't put it on your French fries because you don't have French fries anymore. And you sure, as the sweet Dickens, had not better eat that stuff, because you won't have a face very, very much anymore. So that's kind of what happens. That's like the physical difference between like a strong and weak acid. Weak acids are like yummy and delicious, like citric acid. It's great at the same concentration as a strong acid. It would like the strong acid would like melt our face off, but the weak acids, they like break apart so infrequently that it just sort of doesn't really have that much time to act like an acid, so it doesn't like behave like there's a whole ton of hydrogen ions in there. Do you guys understand what I'm saying? So it's not concentration alone, it's what the things do when you dissolve them in water. Yeah? Alright. So that gives us two words that we really need to dial in here. The first one is dissociation. Now this is when ions break up completely. They break apart. That's it. It's done. They're never getting back together. Broked. It's it. It's like Humpty Dumpty. It's not getting back together. You understand what I'm saying? And you can tell these by this. You see this arrow right here and right here and right here and right here? These are going to be one-way reactions where if you put potassium bromide into a solution, you're going to make potassium. Oh wait, I think I have a thing here. You're going to make a potassium ion and you're going to make a bromine ion. You dig what I'm saying? And that's it. It is a one-way reaction. Here you're going to make magnesium and two hydroxides, right? This guy right here is going to make a hydrogen and one NO3. And this dude down here, is it monodi or triprotic? Do you guys remember that? Of course you do. You guys ain't fools. You're going to make 3 hydrogen ions, right? And you're going to make 1 PO4. Well, let's do this right. There. See how that works? Now, what's important is to know that this is dissociation. And what I want you to see here is we have here is an acid, here is a base, this is your base here, and this is your salt. Salt, basically any ionic compound that's not an acid or a base, because it's the leftovers of an acid or a base reaction. Remember, acid and base makes water and salt. Acid and base makes water and salt. Acid and base makes water and salt. Yeah. So, sorry, because these are all ionic, you're going to have this one-way arrow. It's going to be dissociation, because that's what ions do. Now, let's check out the stuff down here, the stuff that ionizes. Now, ionizing is when they break apart partially. It's like a part-time breakup. It's like everybody knows that couple. We all know that couple. Like one day they're together, the next day they're broken up and arguing and they hate each other. The next day they're so much in love, and the next day they're broken apart, and then they get back together and they break up, and then they get back together and they break up. That's what ionization is. It's like they can't make up their mind. Are they broken apart or are they together? Are they broken? They can't make up their mind. And so, 2 things you got to watch out for that. For us, like as far as deep as we're going with this, there's only 2 things I need you to really clue in on. The first is this right here. See how that starts with the C? See how that starts with the carbon? That is what I want you to look for. I want you to look for the carbons, because carbons are always anything carbon-based for us is going to be considered a weak acid. You dig what I'm saying? And the other thing you need to check out is this, right? You see that equilibrium, the 2-way arrow? If you see that, you know that it's going to be weak. You guys dig what I'm saying? So far, it's pretty simple. Strong, it's going to be ionic, breaks apart completely. It does what we call dissociation. Weak, it's carbon-based. It does what we call ionization, where it only breaks apart partially. So it is not concentration that determines whether we call something strong or weak. It's how it behaves in the water. You guys get what I'm saying on them? I'm sure you do. You guys are pretty smart. So that's like part 1 for today. The other half of what we're going to do for today is how we name acids and bases. And I know naming is like the one thing that everybody hates in the whole wide world, but this is pretty easy, guys. This is not going to be hard. It's not like it was before with the naming and like the Roman numerals and all that kind of stuff. So, here we go. Part 1, naming acids and bases. The first thing we're going to do are the easy ones. We're going to look at binary acids. Now binary means 2, so you're going to have hydrogen and 1 element. Okay, that's it. That's all there is. Now this only counts if it's hydrogen and 1 other thing. And all you do is you say hydro for the hydrogen, right? So the hydrogen right now, you say hydro. That's pretty straightforward, right? Now, your negative ion, whatever it happens to be, you simply end it with ic, which is why it's hydrochloric acid. Do you guys get what I'm saying? Here, let's do a couple. So this good old HCl, that binary 2. Anytime it's binary, you start with hydro. And now here's kind of what happened. How do you spell chlorine? CHLORINE. All right, it was chlorine, right? So you take that ending, that "ine," and turn it to "ic." That's it, hydrochloric acid. You dig what I'm saying? You see how that works? All right, a couple of examples here. HF. All right, so HF, definitely binary. So we're going to start out with hydro. Right? Now the next one is fluoride. But remember, we're going to take the ending and we're going to change it to ic. So instead of fluoride, fluoric acid. Yeah, that's really all there is to it, man. This next one, I see that this next one right here This is again, this one's a binary, right? There's two, just hydrogen and one other thing. So it's going to start out with hydro. And Br is bromine. But we just take that ending, that ene, and turn it to ic. That's all there's to it. You see? Now the next one, iodine. It's binary. It's hydrogen and then some other binary thing. So we're going to call it hydro. Only because it's a binary. Remember, this only works if it's hydrogen and then one other kind of negatively charged thing. So it's hydro, iodine. Turn the iodine to ic, hydroiodic. That's simple. Okay. Now the next one might be a little more spicy. Ternary acids. Now this is something where I might need to like bring in some extra help here. So let me see what I got here. I'm gonna come here. Oh, look at that right there. I downloaded it. Don't tell me you guys don't love this thing. Come on. It's so good. All right, what we're going to need for right now is this thing right here. All right, we're going to need to look at table E because what's coming up are these ternary things where we have three elements. It's going to be hydrogen and a polyatomic ion. Okay? This is actually easier than the first one because look, if there's a polyatomic ion, you just focus on the polyatomic ion. And that is it. And look, man, you guys already know they're all right there. You don't really have to look anything up, okay? So what we do here is the H, nothing, because we already know. You don't worry about it. We're gonna take this polyatomic ion, and the 8 goes to ic, and the ite goes to us, okay? That's 8 goes to ic, ite goes to us. 8 to ic, ite to us. Yeah, 8 to ic, ite to us. 8 to ic, ite to us. 8 to ic, ite to us. This is where I miss being in the classroom because you know what I'm gonna be doing. If I'm in a class, that had a beat to it. You can't tell me that doesn't have a good. That is fire right there. 8 to ic and then ite to us. You can't tell me it doesn't work because it does. It works so good, so good. Anyway, here we go. All right, so HNO2. I see 3 capital letters. So the first thing I'm going to do is go bam right to here. And I'm going to go, oh, right there. NO2 is called nitrite. All right, that's good to know. So I take my 8 to ic, ite to us. I take that ite and I make it us. Now, this is called nitrous acid. That's it. That's all there is to it. You just take 8 to ic, ite to us. That's all. Is it? Like this next one. See the HNO3. Oh, look, NO2 and NO3. See how they're different? Like H2O and H2O2. Yeah, they're really different. H2O and H3O, they're really different. So nitrate. Wait, 8 to. Oh, nitric. You see, I just take the 8 right there and I turn it to ic. That's it. 8 to ic. Ite to us. The end. Oh, wait, well, okay, I have to say acid because, so we know that we're naming an acid, but of course, don't be silly. Of course you know that. 8 to ic, ite to us. Yeah. Okay, don't forget that. It goes 8 to ic, and then ite to us. Got it? Well, that's a lot. How are we going to... Well, they all seem to have at least 3 capital letters. So that indicates to me that there's a polyatomic ion. And if that's the case, we just come over here and we're just going to look up SO3. Where's SO3? I don't even know what SO3 is. I have to find it here somewhere. Oh, sulfites. So I'm going to come back over here and I'm going to write sulfite. And it goes 8 to ic, ite to us. Sulfus acid. I guess, yeah. Sulfus acid. That would be messy, who cares, right? Now the same thing with the next one. What could SO4 possibly? I see 3 capital letters. So if I see capital letters, I'm going to come over here to number 4, SO4, where it says sulfate. And it goes 8 to ic, ite to us. 8 to ic. Sulfic acid. Do you see how hard that is to name acids and bases? Dude, it is not. It is not. As long as you can remember 3 capital letters, go to your reference chart and only worry about the polyatomic ion. Now this one's ClO. I don't even know what that is. ClO. Oh, right there. Hypochlorite. I wonder if I can even do this. Is it going? No, not going to let me do that. Okay, see if I can cheat my way through here. It's cheating. All right, everybody, it's easy. 8 to ick, ite to us. Acid. And it's gonna, I don't know if I can fit it. There you go. See? Are you guys following this? Same thing with CR07. This one is a very strange bird. I have never, you know what? I'm gonna go like this, see if we can like clean these up just a little bit for y'all, because it's getting cluttery for me. So CR07, no idea what that is. We come over here, what? Wait. Don't look. Just look away for a minute. There you go. Don't look. What do you just don't judge. All right. I'm new at this. Don't judge me. I meant to say CR207. That's what I said at first. And then I came over here and was like, "Oh, there it is right there. CR207." All right. Dichromate. You guys know how this works. I won't judge you if you won't judge me. 8 to ick, iced us. Dichromic acid. Super easy, right? That's why pencils come with erasers. My pencils come with a big fat erasers, and I get like a box. You know why there's a box of pencil erasers in my desk? All right, ClO4. I don't even know what that is. I actually don't. Perchlorate. Oh, that's easy. I have no idea what perchlorate is or what it does or anything like that, and I don't even care because I'm just naming it, and I know that 8 to ick and ite to us. So 8 goes to ick. That's all we have to do for naming. We good? Good. That was easy. The very last thing that we're going to do now is naming bases, and this is so hard. You're never going to be able to do it because here's basically what we do. You say the name of the positive ion, and then you say hydroxide. So if it's sodium bonded to hydroxide, you say sodium hydroxide. That's all. But you just say the first thing, and then you say hydroxide. No, that's like that's all of it. See, this is Mg stands for magnesium, and then it's bonded to hydroxide. That is it. The next one, do you see how that's potassium? And you see how it's bonded to hydroxide? You guys want to do more stuff? Want to do more? No? Is it? Okay. So look, let's do it right here. Naming acids. I revised the one that's in your homework packet. I changed it up a little bit to make it a little bit easier for what we're dealing with right here. So same as usual, upload email, whatever, but don't forget, I need to see a copy of the handwritten notes. That'll make all this super duper easy and awesome. Hope you guys are managing to, socially distance from one another and not have too much cabin fever. Hope to see you guys soon, sooner rather than later. Have an awesome day.